This is EC 201, lecture 26. So to continue where we left off yesterday, we saw how you can stabilize the bias current in a PMOS device and make the bias current independent of the threshold voltage of the device. And the methods used are in fact identical to those used with the NMOS transistor, except that the directions of VDD and ground and stuff like that are interchanged. Then we went on to try and figure out how the topologies for the control sources would look like when you use a PMOS transistor rather than an NMOS transistor, and not surprisingly we found that the topologies look very similar. We went through with the voltage controlled voltage source, the voltage controlled current source and the current controlled current source yesterday. The last man standing is the current controlled voltage source. So in other words, you are trying to realize an incremental output voltage which is an incremental input current multiplied by some constant R, and this R is called the transimpedance of the control source, because the transfer function of the control source is an output voltage and an input current, so it must dimensionally be that of a resistor or an impedance. If you were in a lab and wanted an output voltage which would be R times an input current, then what would you do? You would, for instance, have some provision to have a variable voltage source V out, okay, and you compare V out with In times R, which is equivalent to saying I will subtract In times R from V out, so this voltage will become V out minus In times R. Now if I find that V out minus In times R is greater than 0, what does that mean? It means that V out is too high. I have to pull V out down. The only way I have of making V out go down is to yank current out of the node. So in other words, if I had a variable current source, then if V out minus In R was greater than 0, then I should pull current out of the node V out. So this current must be of the form Gm times, if I call this node potential node X, I will call this current has to be Gm times Vx. Okay. On the other hand, if V out minus In R is smaller than 0, or it was negative, then you know that V out is not high enough, in which case I have to push the potential of V out up, and that is accomplished by pushing current into the node. So you can see that the sign of the control source is correct. This is a control source whose current depends on the difference between the potential at node X and ground. I could redraw this in this fashion, and the next job is to recognize the transistor. Okay, this is the incremental equivalent circuit of an NMOS transistor or a PMOS transistor operating in saturation. The last time around we had used an NMOS transistor, so this time we should use a PMOS device. Now can you tell me which should be the gate, which should be the source, and which should be the drain? This should be the source, X must be the gate, great, and which must be obviously the V out must be the drain. We need a PMOS transistor rather than an NMOS one. This is exactly the same circuit we got with the NMOS example, okay, except that the arrow is now pointing inwards to indicate a PMOS device. Alright, so if I redraw it in a slightly different way, this is the incremental equivalent circuit. Okay, now this guy here is the incremental equivalent circuit. Can you now help me figure out what the real circuit should look like? First you must bias the transistor. The source of the transistor must be at incremental ground. Alright. Can I connect the source to real ground? Why? So we expect the current in the transistor, the quiescent current in the transistor to flow like this. And if you connect the source to real ground, obviously current can't flow away from ground if all the other sources are positive. So this must be connected to the highest potential you have. So let's call that VDD. Let's get rid of the input current source for the time being. So what bias technique would you recommend? One way of doing it is to use this bias technique. So this is IREF, and there is negative feedback through here, and this will ensure that the drain current in the transistor is also equal to IREF. You can hook on the input directly if it was a current source. If you want to hook on a load, you follow the usual trick of put an infinite capacitor. So if the GM of the transistor tends to infinity, what is Z in? Okay, how will you figure out what the input impedance is? Push in an incremental current, measure the voltage developed across the port, and that should give you the ratio of the current voltage to current should give you the incremental impedance. What is the incremental potential at this node? 0, because the negative feedback loop senses the difference. The incremental voltage at this node is nothing but the incremental output voltage minus In times R, and if GM tends to infinity, even a small difference between V out and I in R will cause the transistor to kick current into this node here. So the incremental potential here is always 0 regardless of I in. What does that mean? It means that if GM tends to infinity, the input impedance is 0. Is that clear? This is what we did even with the NMOS case, nothing new. What can you say about the output impedance here? The output impedance is also 0. I mean, if you don't understand, then please replace the transistor by its small signal equivalent and go do the math. Physically, you can understand it as the following. If GM is infinity, then we just agreed that this potential is incrementally is 0, which means that this potential, that is the potential here will be I in times R independent of RL. So if you have a black box whose output remains independent of what load you hook on across it, it means that the output impedance of that port is 0. So you can see that as GM tends to infinity, this behaves like an ideal current controlled voltage source or a transimpedance amplifier. And in the last two classes, we basically have gone through with the PMOS transistor what all we did with the NMOS device. So instantly the number of circuits you know have gone up by a factor of 2. So we figured out NMOS, we figured out PMOS. The next thing is to do what? Figure out the two together. As a motivation for that discussion, let's consider a common source PMOS amplifier. Let's assume that the transistor is operating in saturation and some drain current ID is flowing, alright, and the same ID will flow through R. This I will call this say VD. What is the incremental gain from here to here? Minus GM times R. So if you wanted to keep the transistor the same and also keep VG the same, okay, VG is the quiescent operating point at the quiescent operating voltage at the gate around which the incremental signal will hover around. Okay, so if we realize just now that the gain, incremental gain is minus GM times R, and if we want to keep ID and VG the same, the only way of increasing gain is to increase R. Right? We discussed this before also. So, as they always say, a picture is worth 1,000 words. So let's draw a picture and figure and try and understand what's happening. So, if I plot VD on the x-axis and ID on the y-axis. How can I graphically determine the quiescent operating point VD? We recognize the fact that the current through the load resistor is also ID. If I plot the output characteristic of this transistor and the IV characteristic of this resistor, the point where the two intersect should give the is quite you can see that the argument is quite trivial. So the first part is to try and plot the characteristics of the transistor on this graph. We are always used to plotting VSD versus ID for the PMOS transistor, correct? Now I am asking you that this is a slightly different graph. On the x-axis I am plotting VD, not VSD. What do you think the characteristic of the transistor will look like? Let's call this VDD. So when VD is VDD, the drain current of the transistor would be 0. At what region of operation would the transistor be in at that time? If I push VD to VDD, what current will flow through the transistor? We agreed that the current through the transistor will be 0. And what region of operation is the transistor in now? So the triode region. Let's do the other thing, which is when VD becomes 0, what will be the current through the transistor? It will be given by some constant value, which is some, what is this, mu p, 1/2 mu p Cox W by L times VDD minus VG, that is the source gate voltage, minus VTD whole square. Okay, let's call that value I1. When VD is 0, this is the current. When VD is VDD, this is the current. So how will the characteristic look like? It should look like pretty much what you used to, except that it is now flipped left to right, because we're normally used to looking at characteristics which look like this, but that was with VSD plotted on the x-axis. We are now plotting VD on the x-axis, so it must be flipped from left to right. So in other words, the characteristic will look like this. The other part of the problem is to plot the characteristic of we plotted this characteristic, we will plot this characteristic where the two intersect is what we are looking for. So if I plot ID versus VD for the resistor, what will I see? I will see a straight line with a slope of 1 by R, the slope is 1 by R. The operating point is therefore the point of intersection of these two, and as we expect, if the transistor is operating in saturation, okay, the quiescent current through the resistor is also equal to ID. You can read the quiescent voltage off by the intercept on the x-axis, and the slope, since the slope is 1 over R, this must be I times, if I call this I1, this must be I1 times R. We are interested in small signal gain. In other words, we are interested in the change in the output voltage at node VD when the input gate source voltage is changed by a small amount. Okay, so let's say the earlier voltage was VG equals say some VA, and now I reduce VG by a small amount so that the VSG is increased by. In a PMOS transistor, to increase the current, I should reduce the gate voltage. So if I reduce the gate voltage by a small amount, some delta V, then the drain current will increase. And how will that characteristic look like? Will it be above or below this one? It will be above. And what about the value at VDD? That should be the same. So what it should be doing is, when the applied voltage was VG, this was the output voltage. When the applied voltage is VG, which is VA minus delta V, this is the new output voltage. So what is the incremental change in the drain potential due to an incremental change in the gate potential? What is the incremental output on the graph? Okay. This was the quiescent output, this was the output voltage at the drain when Vg was equal to Va. This is the output voltage at the drain when Vg is equal to Va minus delta V. So what is the change in the output voltage? Graphically, what which quantity represents? Okay, which line segment represents the change in output voltage? It is this fellow here. Oops. So it is this line segment which represents the change in the output potential due to a change in the gate voltage. Okay. So if I wanted to find the gain graphically, what would I do? If I wanted to determine the incremental gain graphically, what would I do? I'll find this, then what? I'll divide by delta V. That should give me the ratio of the change in the output voltage due to a change in the input voltage. The change in the input voltage happens to be delta V. So that should give you the gain. Straightforward. Now, if we wanted to get a larger gain, what would I do? I mean, one thing I could do would be, as we discussed yesterday, is to choose a larger resistor, but there is a limit to how large a resistance you can use, simply because if I go on increasing the resistor, I will eventually end up in the triode region. This is the triode region. This is the triode region. And please note that the slope of this line is proportional to 1 over R. So if I had a larger resistor, this will tend to become parallel, more and more parallel to the x-axis. If I get too greedy and try and increase R, then I will end up in the triode region. So to get a larger gain while still remaining comfortably in saturation, what should I do? To increase VDD. Okay, so let me show you. So you can see that if I wanted, say, twice the gain, I had to push VDD virtually almost by a factor of 2. If I wanted 10 times the gain, I would have to increase R by a factor of 10. Alright? Because this slope is what gives me, the lower that slope, the larger the gain is. So to get 10 times larger gain, I would have to make this slope 10 times smaller, which means that the VDD will have to be pushed out by a factor of almost 10. Does that make sense? Now that kind of seems like a kind of a pain. If I wanted, say, 30 times the gain, I would have to, there is no space on this page to stretch this axis out by such a large number. So if I wanted 30 times the gain, but with the original VDD I started off with, can we think of some ways in which that can be done? In other words, let's say we restricted VDD to lie somewhere in this region. We didn't have such a large VDD to begin with, but you want large gain. You don't have a large VDD, so you better you operate somewhere in this green box, but you want gain. If you want gain, the slope of, where the characteristic of the resistor crosses these two lines, the slope must be, if you want the same gain but with a lower VDD, whatever you do, the characteristic of the so-called resistor must cross. To get the same gain, the slope of the resistor must be the same, but must cross much earlier than where it's crossing now. Does it make sense? If the characteristic of your resistor was like this, then you'd be able to use only a small VDD and still get the gain. But now, can this be a straight line? Okay, what will happen if it is a straight line? It is no longer a passive device. Okay, first of all, it's no longer linear also. You understand? If we had some, instead of having a resistor here, if we had some magic box with this kind of characteristic, then it would no longer be, first it would no longer be linear, because a linear two-terminal element, the characteristics must pass through the origin. On top of a linear element, if you want to have a passive element, the characteristics can only be in the first and the third quadrant. So if you had to have the same slope but occurring much earlier than this guy here, then the characteristics cannot be a straight line, okay, because if it were a straight line, it will become active and it will go into the second quadrant. So what do you think you can do? If you think of the ideal characteristic you would want for that guy there. If it has to be passive, it must lie in the first quadrant or the third quadrant. If it was doing something like this here, it must jump into the third quadrant, correct? So it must pass through the origin. What do you think? Should do something like this. Does it make sense? So we are saying that if we had a linear resistor for the load, then to get a very large gain, we need to have a larger and larger supply voltage. Now the next thing is, can we do something about this? Because having a large supply voltage is kind of a pain, fundamentally because it costs a lot of power. Alright, so is there any way of getting large incremental gain without having a large power supply? And then we said that, hey look, this is the part which is giving you gain. The only crime of the resistor is that since its input-output characteristics are linear, if this has to intersect far out, okay, I mean if you want large gain, you want the slope to be very small. If you want the slope to be very small, the only place where this line can intersect these two guys is somewhere far out. And then you say, hey, if I had an element which had a very small slope, but somehow the slope was shifted into the region where the VDD was low, then I would be able to get a large gain without having a concomitant increase in VDD. And then you say, well, unfortunately, that if this characteristic remained a straight line, then that element there would neither be linear nor passive. And then you say, okay, to hell with linearity, anyway we are only interested in incremental gain. Our MOSFET is so badly nonlinear to begin with, so it hardly makes sense to get hung up on a linear resistor. And then you say, well, if I wanted it to be passive, then the characteristic would be something like this, and it would eventually go into the third quadrant. So even though the slope was very small here, the slope should become larger and eventually go into the third quadrant. Does this make sense? So in the limit, when you want larger and larger gain, what are you looking for? If you want larger and larger gain, you were, in other words, looking for something which is like this, and it's passive, so it must do this. So let your imagination run a little wild. Alright, so you want larger and larger gain, you want to make this flatter and flatter and flatter. And now does this ring a bell? Does this characteristic sound familiar? It's an NMOS transistor. And what should the NMOS transistor be biased at? In saturation, the quiescent quantity of interest is the drain current. You must, in other words, an NMOS transistor So how does the circuit look like? I will get rid of this chap. So I need to get rid of the resistor and then put here in its place an NMOS transistor, and the NMOS transistor must be biased so as to carry a current I1. Please note that the PMOS, under quiescent circumstances, the PMOS transistor was carrying a drain current of I1. So this is what I must do here. So can anybody suggest a simple way of biasing the gate source of this transistor? Vg is such that this drain current is equal to I1. Okay. You want this also to carry a drain current of I1. So one simple way of doing it is to use the current mirror, for example. VDD, this is I1. You understand? And now this gives you an incremental gain which is in principle infinity. If this characteristic was flat, which is what you would expect for an ideal transistor, you will get the slope of this would be 0, which means that the equivalent resistance is infinity, which means that the incremental gain you get is infinite. Okay. In practice, you know that a MOS transistor will have some finite slope, so you will get a large gain, but not quite infinite. We'll work out the details, pretty soon, but this is the basic idea. Okay. And this is a very, very common technique and used in ICs all the time with several advantages. It turns out that, though this is not a fundamental thing, that on an IC making large resistors is difficult. And if you wanted to get a large gain, you needed a large resistor, so that resistor would occupy a lot of space. And not only that, you also need a large power supply voltage which would drain off your battery very quickly. So this is called the active load. The name is quite a misnomer simply because the characteristic of this green circle is still a passive characteristic. The reason it's called an active load is because you are operating the transistor in the active region. Now try and find the incremental gain when the transistors are all operating in the active region. The first thing to do when you want to find the incremental gain is to draw the incremental equivalent circuit. So what is the incremental equivalent circuit of the PMOS transistor? The transistor is operating in saturation. The PMOS transistor, this is the source is incrementally grounded because connected to VDD. This the gate goes to the incremental input delta V, okay, or let me call that Vi. In a real PMOS transistor, as I said, you will have some channel length modulation, so let me call that Rp. That represents this 1 over the slope of the IV characteristics of the PMOS device in saturation. Now this goes and connects to an NMOS transistor, to the drain of the NMOS transistor. What is the small signal equivalent of the NMOS transistor? There is the output impedance of the incremental current source, which is 1 over lambda n times the quiescent current I1, and there is, let me call this node X, Gm incremental voltage at Vx. I need to do something else. 3 transistors in this circuit, so you have to replace every transistor with its incremental equivalent. We have done it for the PMOS device, this is done, okay. We need to do it for this guy and this guy. Yeah, so let's consider this transistor now, the one in green. The gate Vx, the gate source of the transistor is, the gate of the transistor is Vx. And is there something, is Vx floating or is there something connected to it? Now we are done with this transistor. We need to find the incremental equivalent of this guy. So what do we have? The drain and gate of this the transistor in green are now shorted to each other. So this is Gm Vx, and the gate is shorted to the drain. So this is exactly the same as Vx. So this chap is this. This guy is the same as this guy. This guy is the same as these two guys there. You understand? And this chap here is this chap. Okay. Now quickly, can you tell me what incrementally what Vx is? 0. Why? Why is it 0? I mean, right, Kirchhoff's current law, this no current flow, so GMVx must be 0. So incrementally, Vx must be 0. So, which means that no current is flowing, so I can replace this by an open circuit. Vx is 0, so this current is also 0. What is the incremental gain? V out by Vi is what now? Look carefully. This is GMP. It's minus GMP times RP parallel Rn. And if you had ideal transistors, RP and Rn would both be infinite. So in principle, if you had ideal transistors, you would get infinite gain. In practice, it's not uncommon to get gain of 100 or so. Okay? And you can see that all that the NMOS transistors are doing are presenting a load to the PMOS device. And you could have derived it another way. We went on saying that the incremental gain is minus GMR. So if you wanted an infinite incremental R, you could have put a current source. And that's precisely what this is. If the transistor is ideal, this is an ideal current source, and that will result in a very, very large gain. Okay. So this is an example of what is called an active load, and as I said, this is repeatedly used all over the place in ICs. Tomorrow actually we'll continue. We'll take a look at the CMOS.